All right, so welcome to Math 150, Section 2, Lecture 7. What I want to do today, since there were no questions on the material, is actually focus on applications of calculus. So the big idea today was the tangent plane. So rather than working with the tangent plane initially, I'm going to talk about the one-dimensional analog. So what do you think the tangent plane is generalizing? What do you think the one-dimensional version of the plane is? The line. So you should hopefully have seen the tangent line before as one of the big ideas in calculus. You replace something complicated with something simple, like a line. We're going to do that here as well. And I'm going to show you an application to what's called the birthday problem. So this is one of my favorite problems in mathematics. So it goes as follows. How many people do you need to have in a room before you have at least a 50% chance that two people share a birthday? All right, so hold on, Kayla. You can speak later. As phrased, this problem is poorly describing the situation. Why is this bad phrasing? What else might you want to know? I want to fit. Yes?
What is a birthday?
Well, you'll be a little bit more specific. So I want at least a 50% chance that two people in the room share a birthday. Right now, with this class, I'm confident, I think. What do you need for the phrasing? What might be unclear? Yes?
How many people are in the class?
So, okay, so one thing is how many, but that's what I'm asking you. How many people do I need before I have at least a 50% chance? What do you think you need to know about the birthdays?
Do you want like same day or same day, same year?
Same day, same year. For instance, for a while, I had bad credit rating because I was amalgamated with somebody who was born in 1950. And I was trying to convince the credit card company, we're not the same person. Look, see the different years. Okay, so we will accept same year. Is there anybody here who was born on February 29? It's not a coincidence. I have a no February 29 policy in my classes. You are allowed to discriminate against people on the basis of day of birth. You can also discriminate on the basis of being a Yankee fan. These are not protected categories on this campus. So I have a deal with admissions that nobody who was born on February 29th is allowed to take any class of mine where I do the birthday problem. Because it just screws up the analysis. So now we'll assume there's always 365 days in the year. But what else do you want to assume about the birthdays?
They occur at the same frequency.
They occur at the same frequency. So if there are identical twins, very high probability you will have two people born on the same day. Anybody a sports fan here or a sports player? All right, hockey players. All right, so there's a great set of quotes in Malcolm Gladwell's book Outliers, where he goes through the Junior Canadian Hockey Championship of one year and replaces the name of players with their birthdays. And it's like, January 14 passes the puck to January 7, January 7 passes to March 7, March 7 shoots, blocked by February 4, rebound by March 3. And you see all the birthdays are clustered in about a 3-month period. And the reason is, for a lot of kids' youth leagues, you want to be the oldest kid to just miss the cutoff. You want to be the oldest kid in the league because odds are you'll be bigger. And if you're bigger, odds are you'll have an advantage, you'll play better, you then get more playing time, the coaches league hire you, and it actually propagates all the way up to professional leagues. Birthdays are not uniformly distributed among professional sports. We will assume birthdays are distributed uniformly. We will leave other questions like that to other departments as to how they might be distributed. We will assume uniform distribution. How many people do I need before I have a 50% chance? So here are some possibilities. 11, 22, 45, 90, 180, 360, and 720. So I want to have at least a 50% chance that two people share a birthday. How many people think 720, that's going to be the first time we'll have at least a 50% chance? All right, Kayla?
I think you'll have to do it.
So do you think that's the first time I'll have a 50% chance? No, why not?
Because you can do a lower number.
What's a low number that's guaranteed to work?
366.
366. So why if I have 366 people in the room, am I guaranteed to have two people with the same birthday? Yes? Yeah, there's only 365 days in the year. I have to double up. So we know 720 is off. 360 is probably off as well because that's almost the entire year. What about 180 people in the room? Do you think that that could be the first time? So 180 out of 365, that's about 1/2. At this point, if we hadn't had a match, the next person walking in would have about a 50% chance of matching with somebody. But it's very unlikely I would get this far without having a match. So the answer is probably much lower than 180. So what I want to do is I want to try to write down a formula for the answer, and then we'll try to analyze it. So let Pn be the probability n people have no common birthday. So often in mathematics, it's easier to calculate the probability that something doesn't happen than to calculate the probability that something does happen. Okay, that was really bad. I tried to touch that while I was recording. All right. So if I have just one person in the room, what's the probability that they don't share a birthday with anybody? 100%. 100%, right? How should I write 100%? 1. There's a better way of writing 1. So much of my life is about algebra. And that's one of the reasons why I want to spend time doing this. I want you to really think about how should you express things to make things enlightening. I'm sorry? Good. But what should n be? Well, what's the natural number to use for the birthdays on Earth? 365. So I could write this as 365 over 365. But I'm a Yale, Princeton-trained professor teaching at Williams. I can do even better than that. I can write this as 365 minus 0 over 365. That's even better. Because now I'm multiplying by 1 and subtracting 0. I'm doing 2 of the great tricks. And I can then write this as 1 minus 0 over 365. Let's imagine a second person enters the room. So now we have 2 people. So the first person can have any birthday. The second person, how many days could they have and not share a birthday with the first? Excellent, 364. Somebody's getting a lunch dessert. All right, so it's 1 minus 0 over 365, 1 minus 1 over 365. And more generally, if we had n people, it would just be 1 minus 0 over 365 all the way down to 1 minus n minus 1 over 365. And it's a little bit annoying, but when we have n people, we stop at n minus 1. I could write this as 365 times 364 all the way down to 365 minus n minus 1. All divided by 365 to the n. What does the top look a lot like? Yes?
365 factorial.
Yeah, so let's just multiply by 365 minus n factorial over 365 minus n factorial, and we get 365 factorial over 365 minus n factorial times 365 to the n. So that would be the answer. That's the probability we don't share a birthday. How many of you have calculators? If you put in 365, odds are your calculator will overflow. Most calculators crap out somewhere between 60 and 100 factorial. So if we actually wanted to multiply this, the only way we could really do it is to be multiply, divide, multiply, divide, multiply, divide. If we tried to do 365 directly on a lot of calculators, it would overflow. One of the nice things is you can actually generalize the factorial function. There's this beautiful function called the gamma function. So gamma of s is equal to the integral from 0 to infinity, e to the negative x, x to the s minus 1 dx. And it turns out gamma of n plus 1 is n factorial. So this allows me to use techniques of calculus and real analysis to deal with a discrete function like the factorial function. And then I can replace this with gamma functions, and there are ways to try to evaluate this. All right. Let's now try to figure out what value of n do I need to make this product equal 1/2. And we will see the tangent line coming into play. So Pn, I can write this compactly as a product. K goes from 0 to n minus 1 of 1 minus k over 365. I need to deal with this product. How many of you have dealt with products enormously in life? Okay, good. How many of you have dealt with sums? If you've taken a calculus class, you've seen Riemann sums. All of integration is based on summation. This is the law of the hammer. Whatever problem I give you, you want to convert to something you know. Do you know any function that takes a product and gives a sum? There is a function you've seen in high school. The blank of the product is the sum of the blanks. What function is this? The logs. So you should have a Pavlovian response. Whenever you see a logarithm, the only exception is maybe if you're going into, say, a third grade math class to talk to kids about how to multiply 3 and 5. Don't take logs then. Otherwise, take logs. If I take the log of both sides, I get the log of Pn. And once you leave high school, you always write the natural log as log. You never use ln anymore. All logs are natural. So you have log of Pn is now the sum. K goes from 0 to n minus 1 of the log of 1 minus k over 365. And now we've converted this to a sum of logarithms. All right, but it's a sum at least. We know how to deal with sums. Let's think about this. K goes from 0 to n minus 1. Which is the easiest value of k to put in here and understand? 0. What's the log of 1? 0. The hope is that k doesn't get too large. And if k doesn't get too large, we're essentially calculating something very close to the log of 1. We're going to do the tangent line expansion. So we're going to do a little bit of an aside now and review what the tangent line is, and then we will see how to use that in the problem. So here's my function. Here's my point x naught. Here is x naught, f of x naught, the point on the curve. Here's the tangent line with slope f prime at x naught. For our problem, f of x is the log of 1 minus x. F prime of x is negative 1 over 1 minus x. The log of 1 minus x, I take the derivative. The 1 minus x comes down below. I take the derivative of 1 minus x, I get a negative 1. What's my point x naught? What point do I want to expand the log of 1 minus x about? About x equals not 1, because then I would have the log of 0. What value of x is it very easy to calculate the log of 1 minus x? X equals 0. We want to expand this about the point 0. The whole idea of the tangent line is you take a point where you know what's going on and use that to figure out what's going on nearby. I know what the log of 1 is. It's 0. So I want to use that information to figure out what's happening nearby. So if x naught is 0, what's f of x naught? It's just 0. And then what's f prime of x naught? That's just negative 1. So the equation of the tangent line, it's just y minus f of x naught is thus your f prime of x naught, x minus x naught. That's the equation of the tangent line. So if you want to put f of x naught on the other side, f of x naught is where I start. This is my instantaneous speed, and this is how much time has passed. So I get y equals f of x naught where I was, plus how fast I'm moving, f prime of x naught, times the time I'm moving, x minus x naught. And for our problem here, f of x naught is 0, f prime of x naught is negative 1, x naught is 0. For us, we get y equals negative x. So for us, that's the tangent line approximation to the log of 1 minus x. If x is really small, the log of 1 minus x is approximately negative x. So we're going to use that to take this nasty expression over here and say, all right, well, rather than dealing with that, what we're going to do instead is we'll have the log of Pn is approximately the sum, k goes from 0 to n minus 1, of negative k over 365. So another reason I wanted to do this problem is it allows me to review some summation notation which we're going to need later in the semester. I'm trying to choose problems that can cover many things at the same time. Any questions up to now? Yes?
Could you quickly explain where the y equals negative x came from?
Sure, because what we're doing is, this is the general formula for the tangent line, and then we're substituting in the values for our particular problem. F of x naught is 0, f prime of x naught is negative 1, x naught is 0. And so we get, for this particular case, y equals negative x. In general, you'll have different things. You need to calculate the value of the function and the derivatives. So now we have a sum. We can pull out the negative 1 over 365, and we get the log of Pn is equal to negative 1 over 365. And then we have a sum, k goes from 0 to n minus 1 of k. So we need to sum the first n minus 1 integers. So there's a beautiful trick. And the story goes back to when Gauss was 5 years old. This is one of the top 5 mathematicians in the history. Teacher was probably having a bad day and wanted to shut the little brats up. And said, add up the numbers from 1 to 100 and then tell me what the answer is. And then instantaneously Gauss raises his hand and says 5,050. If my kids weren't here, I would probably say some expletives. How was Gauss able to do this so quickly? Well, if you take the first numbers, 1 plus 2, all the way up to m, let's call that our sum. If I write the numbers backwards, if you add vertically, what do you get every single time? M plus 1. So you would get twice our sum is m times m plus 1, or our sum is just m plus 1 over 2. So this is how Gauss was able to evaluate this so quickly. So for us, we now get the log of Pn is approximately equal to negative n minus 1 times n over 2 times 365. Okay? So the idea was we somehow replaced the complicated logarithm with a much simpler function. And now we want to choose that critical value of n to make things equal a half. All right? So let n star be such that p of n star equals a half. So this is the value we're trying to figure out. We're trying to figure out how far we need to go in order to have a 50% chance of success. Okay. So we would get the log of 1/2 is approximately equal to negative n star minus 1 times n star over 2 times 365. The log of 1/2 is negative log 2. So the negative signs cancel, and we get 365 times 2 log 2 equals n star minus 1 times n star. Or I can bring the 2 inside the log 2. 365 log 4 is n star minus 1 times n star. I am cheating a little bit. I know what the answer is. That's why I'm doing the algebra in a certain way. I want to solve for n star. What could I use to find n star? So I've got 365 log 4 equals n star minus 1 times n star. What could I use to find n star? How would you solve this? You know how to solve this. You learned how to do this in algebra class. What kind of equation is this in n star? What's the degree of n star if I expand this out? 2. What would you use? You could use the quadratic formula. Rather than using the quadratic formula, I'm going to approximate this as n star minus a half squared. And say, hey, it's approximately 365 log of is about n star minus a half squared. If I square this out, I'll get n star squared minus n star plus a quarter. Over here I have n star squared minus n star. That's almost the same, and this allows me to bypass the quadratic formula. I'm already approximating things. This is not a big approximation. It's not going to change things by that much. Okay? Are people happy with this? If you're not, you can use the quadratic formula. But if I now solve, I take the square root and I get n star is equal to the square root of 365 log of 4 plus a half. So there's my approximation. So the question you always want to know is, how good of a job is the approximation doing? So we can actually put in the value of 365 log of 4, take the square root, add a half. And when you do that, and this is why I had the computer calculate this beforehand, you get the value for that is 22.9944. So we need 22.9944 people in the classroom to have a 50% chance. Looking around, do we have more than 22.9944 people in this class? Yeah. In fact, we have significantly more. I'm very confident that we do it. We even did it in the first class today when there was on the order of 12 or 13 people. Okay. I was quite surprised that it worked. It was only about a 17% chance it would work that time. If you actually do the multiplication out carefully, you get when there are 22 people in the room, you have a 52.4% chance that everybody has distinct birthdays. If you have 23 people, there's a 49.27% chance that people have distinct birthdays. This approximation is damn good. They're not listening. I can use Tom. This is incredible how well it does. This is the power of the tangent line. There's a reason we're teaching you this material. It is not so that you can regurgitate it on homework and exams. It's to use it to solve problems. Can any of you imagine a situation in your life where you will be concerned as to whether or not 2 people in a room share a birthday? Okay, so this is probably an example that we don't particularly care about. But the ideas can be used for a lot of things. In cryptography, there's something known as the birthday attack, where the same mathematics like this is used to try to break codes. So there's really good ideas at play here. And this shows you the power of approximations. How many planets are in the solar system? 8. It is very sad. When I was young, there were 9. Right? I miss Pluto as well. And so whenever possible, I try to help Pluto. And so there's going to be another problem later in the semester where we will need to deal with the planets, and I will include Pluto. So imagine now we live on Pluto, and we are looking for platonic friendships. Okay? Anybody know? Sorry, just seeing who's awake. How many? If you don't want, no, I'm not going to go any further. Anybody know how many days it takes Pluto to go around the Sun? A lot. 90,500 approximately. How would you modify this formula for Pluto? What search and replace would you do? Switch 365. So if you have d days, it'd be the square root of d log 4. That's why I was deliberately not multiplying 365 by 2. That's why I was moving the 2 inside the log 2, so that I could see how things depend on 365. And so if you want to do Pluto, what happens now is you get the predicted answer is, I think, 354.2 days, and the actual value is 354.47. So it does a phenomenal job. It gives you the correct growth rate. The growth rate is like square root of the number of days. And this is the power of the tangent line. There are many other applications I can give you of the tangent line. I just wanted to do some motivation. Since nobody said that they had issues with the reading, this gives us time to really dwell on other applications. All right, so we are running on low battery, so Hopefully it will continue to record. If not, we will switch to section 1. All right. So what I want to do now is I want to talk a little bit about the definition of the derivative, and then talk a little bit about what would it mean to modify this for several variables. So I'm going to start off with the standard definition of the derivative that you've seen. F prime at x naught is the limit as h goes to 0 of f of x naught plus h minus f of x naught over h. I think this is the definition that most people see first. There's a tweak of this which is almost the same, which I can then write immediately. This is the same as the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. Just think of x as x naught plus h. And then these two definitions are the same. What I want to show now is a stranger definition which generalizes. The real issue we're going to have in multivariable calculus is we want to discriminate a little bit. We want to say these are the good directions, the x-axis, the y-axis, the z-axis. And we're going to take partials in those directions. Just because those partial derivatives exist does not mean the function is differentiable. If they exist and are continuous, then the function is differentiable. So this is going to be the good definition of the derivative that will generalize. It's the limit, we want the following. The limit as x goes to x naught of f of x minus f of x naught minus f prime of x naught times x minus x naught divided by x minus x naught. And we want this to equal 0. So at first when you look at this, it seems absurd that this should be the definition of the derivative. So the numerator and the denominator, let's look at the denominator first. Well, that's the same as the denominator here. Essentially, what we're doing is we're taking the f prime of x naught, moving it over to this side, and subtracting it. And then since the denominator is x naught, we multiply by x naught over x naught minus x naught. Another way of viewing what we're doing is over here, we're subtracting the tangent line approximation. F of x is where I am. F of x naught is where I started. F prime of x naught, that's my instantaneous speed, and this is the elapsed time. So what I'm saying is my tangent line approximation should be really good to where I am. How good? It should be good relative to x minus x naught. If x minus x naught is small, then almost any approximation is good because there's no movement, right? If I know how far your car is, and I want to approximate its distance from home 1/4 of a second later, just say it hasn't moved. You're not going to be off by much. Does it matter if your car's traveling at 0 miles or 50 miles? No. We're talking about 1/4 of a second. I can't measure distances that small. What I want to do is I want to look at not just the difference, but the relative difference. How close is it relative to how much time has elapsed? So I would want to see how far am I from my initial distance relative to 1/4. And the idea is this is supposed to be so good that this difference tends to 0. If your function is twice differentiable, the area term here is going to look like x minus x naught squared. And so when you divide by x minus x naught, it's still going to be small. Okay? So this is the notion that generalizes. And the real notion of what it means for a function to be differentiable of several variables is that the tangent plane approximation does a great job. That's what's really going on. Okay. So what I want to do now is I want to look at some really painful, nasty limits. Okay? And just use this as an example of how bad the subject can be and why we have to be careful. So I think in the video we look at the function, xy to the 1/3. I want to look at the following. The limit as xy goes to 0, 0 of x to the 8th plus y to the 8th over x squared plus y to the 8th minus x to the 10th plus y to the 10th over x squared plus y to the 10th. Wonderful, wonderful thing to look at. I spent some time 2 decades ago coming up with this example. You only have to come up with this example once in your life. Right? What should you do to try to calculate this limit? What should you do first? Yes? In what sense? So one is you could try to break it up as 2 different limits. You have to be careful, though, that only works if you know if each limit exists. So the limit of a difference is, you should always be thinking to do that, but you need each limit to exist. It's possible that maybe each limit doesn't exist, but they cancel each other out. So that is definitely one thing you could try. What else could we try?
Simplify.
We could try to simplify. Unfortunately, algebraically, it does not simplify. When you're trying to calculate limits, what do you do first? What path do you do first? X-axis, y-axis. This should be your Pavlovian responses, okay? Whenever you see a limit, take x equals 0, take y equals 0, then take y equals ax if they're the same. When you see a product, take a logarithm. If you see Professor Miller's kids, compliment them. Right? These should be instinctive things to do. Okay? Let's take y equals 0. So if y equals 0, we have x to the 8th over x squared. That's x to the 6th. What does x to the 6th go to? It goes to, not infinity, 0. We're sending xy to 0, 0. So if y equals 0, x has to be going to 0. So I've got x to the 6th. X to the 6th goes to 0. On this side, y equals 0, I have x to the 10th over x squared. That's x to the 8. What does x to the 8 go to? 0. So the limit is just 0. All right, let's try x equals 0. Now I get y to the 8th over y to the 8th. What's y to the 8th over y to the 8th? 1. Right? Y to the 8 divided by y to the 8 is 1. What is the limit of 1 as y goes to 0? 1, which doesn't change. On this side, I get y to the 10th over y to the 10th. That's 1, so I get 1 minus 1. It's still 0. How many people think the limit exists? All right, let's try y equals ax. So now we get the limit as x goes to 0. So y equals ax. We have x to the 8th plus ax to the 8th. So we get 1 plus a to the 8, x to the 8. Now down below we have x squared plus a to the 8, x to the 8. So it's 1 plus a to the 8, x to the 6th, x squared. I'm just factoring out the x squared from below. We have x squared, a to the 8, x to the 8. Is everybody happy with this algebra? If not, I just urge you to go home and just go through this very slowly. I'm just letting y equal ax. So we have x squared plus y to the 8th becomes x squared plus a to the 8, x to the 8. That's just 1 plus a to the 8, x to the 6th, x squared. Okay. The other one, just to save a little bit of time, is going to be 1 plus a to the 10th, x to the 10th, over 1 plus a to the 10th, x to the 8th, x squared. You can see now why I wanted to spend the time and pull out the x squareds. X to the 8 over x squared is what? X to the 6th. What does the denominator go to once I pulled out the x squared? What does 1 plus a to the 8 x to the 6th go to? 1. That goes to 1 plus a to the 8th. We have an x to the 6th. So what does this whole expression go to? 0. What does this expression go to? 0. So we get 0 again. Are you now convinced? I've done it for every line. Are you convinced yet? Fine, I will do quadratics. So x equals y squared and y equals x squared. All right. In the interest of time, I will just say the algebra works and you get 0. Are you convinced now? No. No. Right? He knows me. Right? When I try to go into the 5th grade and do math games with them, the 5th graders know not to trust me. 3rd graders still trust me. They'll learn. Well, okay. Some 3rd graders don't trust me. So You have to remember the Miyagi secret of multivariable calculus. It must be true for every limit path. Even if I check infinitely many, I have infinitely many more to check. I feel divinely inspired right now. The method of divine inspiration is wonderful. You write down the answer and you show that it works. It's risky to rely on it on exams. You don't know when you will necessarily be divinely inspired. But all I have to do is find one path that doesn't have the same answer. And so given that I constructed this problem, I know exactly which path to look at. Let me try x equals y to the fourth. So I now get the limit as y goes to 0. Now the first one, I will get y to the 32 plus y to the 8 over y to the 8 plus y to the 8 minus the second one will be y to the 40 plus y to the 10 over y to the 8 plus y to the 10. So it's not y to the 8. Yeah, it is y. Okay. So when I look at this, I've got a 2y to the 8 down here. I have a y to the 8 up top, so I can pull out a y to the 8 and have it cancel. And this will become the limit as y goes to 0 of y to the 24 plus 1 over 2. And the second one, I can pull out a y to the 8, and I'll get a y to the 32 minus y squared over 1 plus y squared. And again, if I'm going through the algebra a little bit too quickly, you can just go through, and I strongly urge you to just do it at home. What is y to the 24 plus 1 over 2? What does that go to? 1/2. What does this expression go to? 0. So I get that this is 1/2, which is not 0. Very carefully worked out to be in exactly the same line as 0. The limit does not exist. But it exists. The limit exists along this path, but the limit you get depends on the path you take. Even though along straight lines and along parabolas, even along cubics, you're going to get 0. If you go to a quartic, you won't. The point of this is just how careful we have to be about limits. It's not enough to check certain paths. What we're trying to do is we're trying to have a couple of specialized directions that we care about and say, we're going to take partial derivatives in the x-axis or the y-axis or the z-axis. And we want to build this up to the function as differentiable. But it's not enough for those partial derivatives to exist. If they exist and are continuous, then we're okay. It really comes down to, we want the tangent, was it erased? No, it's over here. We want the tangent plane to be a good approximation. And for the tangent plane to be a good approximation, we're going to need some kind of generalization of this. Okay? So this leads into the correct definition of what it means for a function of several variables to be differentiable. Right. So I'm going to just first quickly review the notation for partial derivatives. We've done this before. For partial derivatives. So partial f with respect to x means the limit as h goes to 0 of f of x plus h y minus f of xy over h. And you could have a generalization of this to 3 variables or 4 variables, etc., etc., etc. You could also write this if you want as the limit as h goes to 0 of f at v plus he1 minus f of v over h. I've got to be careful. I can't divide by a vector. That's why I'm being very careful to say I'm taking h steps in the direction of e1. Later on, we will discover an object that has a really good name called the directional derivative, where the directional derivative is like, well, rather than just saying you step along the direction of x1 or x2 or x3, just step in any fixed vector, in any fixed direction. And there will be a way to relate the directional derivative to the standard partial derivatives. The other notation we sometimes use for this is f with a subscript of x. In one variable we used primes, but because we could have more than one variable at play now, if you say f prime, it's not clear, well, what am I differentiating f with respect to? Here I'm differentiating f with respect to the variable x. Okay, so if I write fxy, this means the derivative with respect to y of f of x, or the derivative with respect to y of the derivative with respect to x of f. So you first take the derivative with respect to x, then you take the derivative with respect to y. If you could choose the laws of mathematics, what would you want fxy to equal? Fyx, absolutely. So this is the hope, that this would be the same as fyx, that the order in which you differentiate does not matter. It's true if your function has continuous partials. And this goes back to general theory from analysis. The smoother things are, the more continuous things are, the nicer things are. I brought Rubik's Cubes to the first day of class. If you do the same sequence of moves, it's a shame, Caleb, we can't do the up, left, down, right now. But if you do, I know. If you do the same sequence of moves, if you have the same set of moves but do them in a different order, you will get the cube in a different configuration. Order matters. The square root of a sum is not the sum of the square roots. Order matters. Most of the time, order of operations matters. It's really nice when it doesn't. And the hope is to have problems where the order will not matter. All right, so in terms of just notation, we're going to define what's called gradient, which is going to be the collection of partial derivatives. So we write it as a triangle. That is df, dx1, df, dxn. So this will be the vector of derivatives. Okay? And the hope is that if the function is differentiable, then we can get a full derivative from this. So I'm going to just briefly end with tangent plane. So let's consider z is a function of two variables, x, y. And we'll say maybe z naught is f of x naught, y naught. So we want to calculate the tangent plane. What do you think the tangent plane should reduce to if I keep y constant? What should it become? It should become the tangent line. And what do you think the tangent plane should reduce to if I keep x constant? No, it's okay. But now I'll allow y to vary, but now x is constant. Another line. So whatever I have for the tangent plane, it should reduce to the tangent line with respect to x if y is constant, and it should reduce to the tangent line with respect to y if x is constant. So this gives me a really good guess for what the tangent plane should be. Z minus z naught should be df dx at the point x naught and y naught. So we often put the point here to tell you where to take the derivative, times x minus x naught. This would be the tangent line if y is constant. Because now df dx, that's playing the role of my f prime from before. This is where I am, this is where I started, this is my instantaneous movement, and this is the time elapsed. So this would become the tangent line if y is constant. If x were constant, the only change would be that this is now 0, and we would now have df dy. So we'd have plus df dy, x naught, y naught, y minus y naught. So this is the only thing the tangent line could be. It has to reduce down to, the tangent plane could be, it has to reduce down to the two tangent lines. Okay? So I will end with just trying to recast this into the standard format. And so we're used to the following equation of a plane. Equation. Well, maybe it's a little weird to say we're used to, given that it's only been 2 weeks into the semester, but it feels like a long 2 weeks. N dotted with x, y, z is some number d. And if you look at what's going on here, the normal vector is going to be df dx, df dy, and then negative 1. And the reason for the negative 1 is because over here, we've got the z minus z naught on the other side. So when we move this to the other side, we'll have df dx, df dy, and then a negative z minus z naught. And that's why for the equation of the tangent plane, that's why we get the negative 1 over here. All right, so this is a good place to stop.